Hey there, folks. Welcome to our final module for CS 4910, Computer Graphics, Introduction to Techniques for Non-Interactive Rendering. We are going to dive into it and wrap things up in what's been a really fun but a quick semester in Summer 2 here. And just as a reminder, just looking at the calendar here, I'm going to highlight here, make just a little bit smaller so you can see the dates, but homework 4 is going to be due at the end of class, as well as the final project. If you do need to use your tokens, you are welcome to, so that you can finish things up in the class. But otherwise, I'll have a relatively quick turnaround time because, well, grades are due really fast in Summer 2, which is I don't know if it's a good thing or a bad thing, but again, it just means that we have to sort of wrap things up relatively quickly on time, but most folks have been doing fine, so I don't have any worries about that, and really looking forward to looking at your final projects. And with that, let's go ahead and dive into the wrap up here. Finishing up some of the topics here. We can take a look at the slides, which I have open here, and let's go ahead and dive in. All right, so what do we have here? Well, a final pre-class warm-up. A few weeks ago, I was mentioning while I was attending SIGGRAPH that I wanted to update you on some notes that I had, and some of the sessions that I found that were really interesting were rendering engine architecture for games. There was sort of a two-part series there, as well as advances in real-time rendering. So these are focused more on real-time rendering, but I think of interest to a lot of folks who took graphics, or maybe you're going to go and take on the graphics. So the link here to the session can be found. Usually what happens in SIGGRAPH is they will update these. So you'll have to search around a little bit. Sometimes you have to wait a little bit, but you can find the 2020 versions for now in the advances in real-time rendering, and I believe there's an equivalent advances in real-time engine architecture here. So they'll link those here, and again, usually you can click on these links and see the actual sessions here. So I'm just going back, trying some old ones, and maybe they're not going to work here, but a few of these will work and give you actual syllabus. So at least you'll have those, or you can search for the PDFs. If you have trouble finding those, please let me know, and happy to help there. Now, the second link that I have down here is something that is readily accessible. They have a Frontiers session here. So when you go to this page, you have to scroll all the way to the bottom here. But they have a bunch of sessions on ray tracing, which might be good as a reminder of what we covered in this class, as well as some new things that might get covered as well. There was a series of about 7, I believe, lectures here, or 8, and just you get to hear from Shirley, some other guest speakers that they have in the talk on this topic here that may be interesting. And then for those folks who say they're totally tired of graphics, I think this will be interesting to see the machine learning stuff with a little bit of a graphics / image processing hint to it, so you can check those out there. All right, so that's just a little bit on the pre-class warm-up. Let's go ahead and dive into our finish here. Okay, so last time you got to look at the state-of-the-art in ray tracing, some of these Pixar research papers, and we looked at one here, and I think it was quite insightful to actually get to see what folks are doing in industry, what is the state-of-the-art, what is considered sort of new at the time. Of course, we looked at a paper that was a few years old, but where they were introducing ray tracing. So I thought this was interesting. It was an interesting exercise. I'd love your feedback if that's something you would have liked to have seen more in the course. That is something that I'm thinking about, if this paper should, or if this course should be more on reading some of these papers along the implementation. So with that, for a second, I am going to just go on my other screen, if you bear with me, and I want to bring up some of the papers that some of your classmates who have completed the activity have completed and written about here. I'm going to hide your names, that's why I'm doing it on the other screen here, but just briefly want to show the responses, because I think this was sort of interesting, and you might have to pause the video and zoom in a little bit, but let me hide folks' names here just for anonymity purposes. But here were a few that folks brought in here. A paper on deep learning and super resolution, which seems cool, and you have the links here, and then another one on path trace surfaces, so subsurface scattering. I think this is pretty cool, and you can sort of explore this. So I just wanted to share with a few of your classmates who are on the ball and knocked this activity out right away, which is awesome. But that was on the sort of research part. So again, hopefully that's a great resource for you and helps you define what some of your future interests or areas that you want to specialize are in graphics. And then finally, we talked about threading a little bit, parallelization. So not to step on the computer systems course, but a thread is a separate sort of logical flow of execution, meaning you can have multiple threads running in one program that share memory. Typically, threads will share memory, and they can work together or cooperate to solve some problem. In our case, rendering an image or testing for intersections, for example. And that tends to be a very parallel problem, especially if you're working on separate pixels and not going to have pixels in overlap or rays cross into each other. Now, again, you might have some of these secondary rays do that, but that is the idea with threads. So that can be potentially very massively parallel. We looked at one example where we saw a 3.5 times performance increase. So you can look at P threads if you're in C, or the C++ has the thread library. Python has threads in it. I believe Rust and some of these other languages that folks are using have native threads. Kotlin has threads through the JVM. So lots of different tools that can be used there. All right, so with that said, let's go ahead. Of course, we're recording. You know about the logistics. Stuff's due soon because we're at the end of the semester here. And today's takeaways, right? We got to really do two things. Just get some feedback on the course and wrap up the course, okay? So this is really ray tracing, the rest of your life, I guess. Evaluation. So let's get this out of the way. Most of you know about this at Northeastern. Put myself on the screen again. But the idea here is, oops, I guess it took me back to the beginning. Evaluations are really, really important, especially for a new course like this, to get some feedback. I'm going to use this feedback to improve this course in the future, other courses I teach, graphics, and so on. So please do, take 10 minutes or 5 minutes to fill out the trace evaluations. It certainly helps me out. It'll help out your future colleagues, and it'll help yourself out if you have me in a class later on. So again, they're just important. So if you're watching this far, go ahead and click the pause button for a moment and fill out the trace if you haven't. All right, and if you've gone ahead and given yourself a few moments to fill out the trace, we'll go ahead and move along here. So I'll get rid of myself here, and thank you for filling out that trace evaluation. And let's dive into it. The course wrap up, kind of wrap things up here. And the reality is, again, this is a brand new course, and it's really an effort to expand what we do in computer graphics. So I'll go ahead and put myself, maybe just me here, to talk about this. But I really think we need more graphics courses, more sort of stuff for folks interested in this industry, whether you're going to go into VR, entertainment, graphic design, whatever it might be, maybe not necessarily specifically game design or sort of hardcore rendering or rendering engineer, but if that is your path, we need some courses to do that, or at least to help exercise some of these skills, exercise some of the math as well. I think it's a really great way to apply it. So I hope it was an enjoyable course from that standpoint. And what I'm going to do now is take us back through the last 12 modules that we did, or rather 13, I guess, with this one, and reflect, as well as have this slide deck be sort of a quick refresher if you need an index of what we covered, along with the website that'll still be there. Just to have everything in one place. I've always found that that's sort of nice. So you can use this as a cheat sheet or sort of build from it. But where we started in module 1, we got our course introduction, some examples of ray tracers, even a photon mapping here. Before you knew it, everything was just ray tracing. So backwards ray tracing, forwards ray tracing, and a little bit on real time, where you get to see this stuff used. And then in module 2, we jumped into, well, just figuring out what color is. So this course, compared to the other computer graphics course, you may have noticed, for those who took both, is, while there is overlap in topics, I wanted to dive a little bit deeper into some of these things. So how we perceive light, what is color, what are the different color models. There are ranges beyond just 0 to 255, right? There's high definition ranges and these sorts of things, so we can get really crystal clear images again. It's nice to have that sort of perspective. Then module 3, we went into our first rendering technique, which was the backward ray tracer, this idea of casting rays from our camera to each point, and that this is different from rasterization, right? This idea of casting rays and testing for intersections and then figuring out how to fill in shapes based off of that. Okay. We also learned about how ray tracing is a really cool technique because we can sort of simulate how light works, okay, and bounces around in that sense. Okay. And then we looked at what was my implementation of a ray tracer to sort of get you started off. Then we dived into some more mathematics, in particular some important tools like dot products, talking about things like projections, normal vectors, some of our tools, these things that just kind of keep popping up in computer graphics that are really your foundational tools for doing anything in graphics, understanding these mathematical tools and hopefully trying to visualize them a little bit. Then we talked a little bit about cameras, just introducing the perspective camera, as well as introduction of materials and thinking about things from these sort of physical properties of things. So physics is actually a really, really great area to dive further in as a graphics engineer. Sort of approaching mathematics as a physicist, thinking about properties, what happens in the real world, and how light bounces around and how light is absorbed, and a little bit of, although we didn't really use calculus, but the sort of the calculus behind that in a sense. Then in module 5, we talked a little bit more about how cameras work, this idea of, how a physical camera works, and that's what we're really simulating in our ray tracers, some of these properties that'll help give us different shots or viewpoints of the things that we're building, some important functions, so we can sort of move our camera around. The look at function was part of your homework later on. And then we started thinking about things like the image quality, improving image quality with anti-aliasing and depth of field for sort of this nice motion picture effect there. Okay, and then we dived into performance, this idea of using profilers to find out where your code is running slow. Here's some of your results. I actually updated this with everybody else so you can see the different languages that people were using and profilers and so on. But this idea that you want to use a profiler, figure out what's expensive, and sort of led us into some of the other stuff later for our accelerations structure of where your programs are spending time. And then we got into module 7, which is talking about what ray tracer is really doing, talking a little bit more about intersections. We got a little bit into the math, talking about primary and secondary rays, again, what the benefits are of ray tracing as opposed to rasterization, this sort of strategy. And then, again, getting a little bit more into the math derivations, pieces where I felt the Shirley text fell a little bit short in explaining what exactly is going on, introducing some of these terms, implicit surfaces, parameterized surfaces, some of these things that would be useful for us, and lead us directly into module 8, which is where we discussed ray triangle intersection, getting ready for our homework, our final sort of homework where we are rendering object models, which is pretty cool. But again, just understanding this ray triangle intersection, which is really ray plane intersection, to test if a ray passes through a plane, and then testing if it's within the boundaries of a triangle. So we saw this neat sort of inside-outside test that we could do to help solve that problem. Okay, and then we talked about one geometry format, the OBJ file format. So again, this one is familiar to folks who took the other graphics class or new for others. So depending on what order you take the classes in, you'll have an easier time with this, assuming you take both. But just how geometries organized, and some pointers into having lists of basically the faces stored, lists of the vertices and the normals, as well as the texture data as well, which a few folks have been doing for their final project, extending this to render textured models, which has been cool. There's been at least 2 folks who have done that. Okay, then module 9, we sort of jumped back into two topics, revisiting image quality and talking about motion blur, because it's a relatively easy thing to implement by being able to move these objects, and then when we're sampling, well, as they're moving, they're going to blur anything that's not stationary, so you can kind of get this cool motion blur effect here. Then we started doing a little bit of measurement. Module 9 is really about our accelerated data structures, so part of the in-class activity, capture some information about your rendering time, and then we talked about bounding volume hierarchies, which I know at least one person is doing, implementing this for their final project, and how to speed up your ray tracers. So this idea of a bounding box or a convex hole, something that wraps around the shape of the object, and you have different ways to make this more accurate. Here's an axis-aligned bounding box, which we talked about, which wraps around much more compact or more tightly here, and how, since most of the rays were shooting out, especially in a very sparse scene, aren't intersecting with anything, so it can significantly improve the performance of our programs here. And we could go beyond doing this by building a volume hierarchy, so we know if some shape here, like this this ogre here, for instance, well, if it doesn't, if rays that we cast don't intersect with the ogre, then we don't have to test any of the other shapes, which is the idea there. All right, then module 10, we talked about texture, so adding yet more detail. Textures being these things that we can wrap around our objects to provide more detail, and then sample from these textures, whether these are pre-generated or procedurally generated with some sort of algorithm. That's the idea, that we can wrap these around these shapes here. And there's different ways to do it, different types of maps. It's an age-old problem. How do you wrap or draw around a sphere here? You get some distortion in some of these ideas, but that's okay. We learned about some techniques for procedurally generating textures, which Perlin noise being the big one here. That's what's shown here in this sort of grainy looking noise here. And then finally, we introduced a little bit about lighting, so emissive light, so having a material that can cast more rays out from it and use that as a light source. Module 11, we sort of had a big surprise where we figured out that we were doing ray tracing backwards, but we want to be able to maybe simulate other effects here in another technique. So sort of our second technique is photon mapping. Okay, it's a two-pass algorithm, another candidate for a final project, with the idea that you can simulate more advanced effects by casting rays from the light source exclusively, and then casting other rays essentially from your camera, and then finding out which of those rays intersect your shape, and then you'll have the actual color on those shapes of the intersection based off of where the light is coming from. Okay, so it's very useful. It's a two-pass algorithm, but it's significantly more expensive than our regular ray tracing algorithm. All right, then module 12 is, I already recapped at the beginning, was looking at some research papers and learning a little bit about parallelization and how that can be applied. And with that, that's it. That's, that's essentially the end of the course. Let me bring myself up here one more time. It's smaller. So some next topics after this course, right? We've covered a lot. We've learned a lot. You've read at least two of the books, the Shirley books at this point, or skimmed through them, as well as hopefully the third book while you're looking for your final project topics. So one of the next places where you can really go here is book 3 of the Shirley books. Okay. That's a great place to continue extending your ray tracer, picking one of those topics and sort of diving a little bit deeper into some of those suggested topics. And then if you haven't taken CS 4300, 5310, which about half of you have, that's another great place to look. So start looking at OpenGL. LearnOpenGL.com is a pretty good website for learning the basics here. And would also get you ready for that course if you're taking it with me, and I'll see you in the fall. But otherwise, I recommend, keep specializing, keep trying to learn and do a sort of deep dive into something that caught your attention. Maybe it was textures, maybe it was the optimization part with the volume hierarchies. When you dive deep into something, and this is a great class to do it because you can render some special effect and keep going deeper and deeper and deeper to the point where you're the expert, right? It's sort of like doing a PhD in a sense. But as you dive deeper and deeper and practice that, you're going to encounter, more advanced mathematics that you have to learn, more things in code and programming techniques that you have to learn. And that'll translate more broadly to other things. So say you want to get really, really good at, say photon mapping, you want to go back and actually implement that. Well, once you implement that, you'll sort of have this idea of, okay, what does it mean to be a two-pass algorithm? How do I sort of structure things in that way? And then maybe you'll say, well, it's not fast enough. And then you'll sort of look at optimization things, or it'll lead you down this path where you just kind of keep learning more. You'll say, okay, I learned about caustics. What else can it do? And then you'll find out there's lots of other different techniques that'll get you closer, right? As you try to implement true global illumination, right? So beyond photon mapping, and learn about different path tracing techniques, different things like radiosity and so on. So that's my recommendation, to try to, keep specializing, pick a particular area that was interesting. Maybe it was in the textures or whatever, and build another project, essentially do another final project, build up your portfolio. That'll make you stand out from the crowd as a graphics engineer and improve your skills overall as a computer scientist and an artist in this class. It's computer graphics, computers and graphics, computer and art. Okay. So those are some topics to look into after the course here. If you enjoyed this course, right, you got the third Shirley book, and then you also have the PBRT book here, which dives into more things. This is a cool book. It's an Oscar award-winning book, which is kind of interesting in itself that a book's won an Oscar, but it's available for free here. Let me try to find the link where I click on it so you can see the different chapters here. Let's see here, full contents, and this is the third edition. I think they just had another edition, but you can see what some of these topics are, right? They've got a framework, but you can see about camera, or if you were interested in textures, different materials, different other things that are interesting, right? Light transport, volumes, etc., that we might not have done a deep dive in this course. They're in this text and a good starting resource for something that works. Okay. So highly recommend doing a deep dive there. Some final projects, I'm going to share those with Piazza. Normally we would do a sort of show and tell together with your portfolio videos, but if you're still working on those videos, make sure to finish those up, upload them to YouTube, view them incognito to make sure that I can see them on the link. Otherwise I'll send you an email, so you still got some time to knock those out. And I'll put those on the sort of slideshow here, so you can see your classmates and what everybody did here. Okay. Other than that, let me go ahead and hide here. Just open constructive feedback on the class. That's what the in-class activity is going to be, or on Trace if you still haven't done it. What were your thoughts of this class? Did you want more structure? Did you want more sort of hand-holding? Or did you like following the Shirley book and sort of working from that sort of framework and having control? In my other graphics class, I provide a lot of sample code. This course I provided much less in sort of the technique or what the goal was. Did you want more research papers? Do you think it would have been beneficial if you were all using the same language? Or did you really like that part because you finally got to do a course in whatever language you wanted? Did you think that this course was more or less enjoyable, not having done the other graphics course? That's something to think about. It's maybe hard to require. Maybe you like the flexibility or whatever, but that's something I'd be happy to hear more about. So just some ideas of things that I would love feedback on, either in the in-class activity, on Trace, wherever, in an email, whatever it might be, that is fine with me. And the last sort of, farewell here, with our little assignments here. So let me pop up me here, small here. Thank you for being a wonderful class. This is a fun, super fun Summer 2 class. Normally we'd be able to get together with a class picture, perhaps in the fall. Since this is a small class, we will try to recreate this or do something interesting, since we never got a full real live session in. But yeah, it's been my pleasure. I hope you enjoyed the course, and we'll hope to see some of you in the future, in future classes, or just stop on by the office. And for those of you, if any of you are graduating and haven't made that aware to me yet, good luck. Let me know what you're up to, and of course always stay in touch on the 000 board. That's where I'll keep posting opportunities for you folks. All right, that's it. Some of you probably want to work on your final projects right now, and then others have, if you're done, you're done, and you can look forward to watching what your classmates have done. Okay, so we'll see y'all soon, folks. Thanks for a great class. It's been my pleasure, and I hope you've learned a lot.